91 ferritic steel containing 9% chromium, 1% molybdenum, and 0.1% carbon is widely used because of its good strength, creep resistance, and radiation tolerance. During additive manufacturing of this steel, martensite forms because of rapid cooling, and the extent of tempering of martensite significantly affects the mechanical properties of parts. Currently, there is a lack of quantitative understanding of the tempering kinetics and the resulting hardness variations. Here we evaluate the tempering kinetics and hardness variation using a heat and fluid flow model, a Johnson Mehl Avrami equation-based kinetic model, and experimental data on aging. We have recently published this work in the Journal of Manufacturing Processes, and we provide a reference to this work at the end of this talk.
Grade 91 steel is a ferritic steel and is a good candidate for structural components in the nuclear energy industry. This steel is extensively used in wrought, welded, normalized, and tempered forms. Additive manufacturing of this steel is gaining attention. The steel forms martensite because of rapid cooling during additive manufacturing. The CCT diagram of grade 91 steel shows that the critical cooling rate for forming martensite is only 0.05 Kelvin per second. Cooling rates during additive manufacturing are much higher than this critical cooling rate, resulting in the formation of martensite. However, repeated heating and cooling during the deposition of multiple layers during additive manufacturing tempers martensite and significantly affects the mechanical properties of the final part. In our approach to explain the tempering kinetics and resulting hardness variation, first a neural network was trained using tempering data on grade 91 steel collected from the literature. Then the trained neural network was used to generate high quality tempering data for various combinations of temperature and tempering time. The constants in the JMA equation were calculated using the tempering data obtained from neural network. A rigorously validated transient three-dimensional heat and fluid flow model of directed energy deposition was utilized to compute thermal cycles at various places in the part. Then the JMA equation was integrated by cumulatively adding small isothermal time steps over a computed thermal cycle to estimate the hardness. Because the hardness variation in a component is directly related to the fraction of phase change to another phase, the extent of tempering was computed from the calculated values of hardness. The thermal cycles were computed using a well-tested three-dimensional transient heat transfer and fluid flow model. Here we show the three-dimensional temperature and velocity field during the deposition of grade 91 steel using directed energy deposition. Near the front of the molten pool, isotherms are compressed. However, due to high scanning speed, isotherms are elongated near the trailing edge. The deposit exhibits a curved top surface formed due to the accumulation of powders. The deposit height is maximum at the center of the fusion zone and it decreases with the distance from the center. Black vectors represent the velocity of the flow of the molten material. The flow of liquid metal occurs along the curved top surface of the molten pool from the mid location, where the surface tension is low, to the boundary where the surface tension is high. Thermal cycles were computed from this 3D transient temperature field. The computed thermal cycles were rigorously tested using independent experimental data. The good agreement between the computed and experimental results provides us the confidence to use the computed thermal cycles for evaluating the tempering kinetics and the hardness variations. Computed hardness variation along the deposit height for a 10-layer high thin wall agrees well with the corresponding experimental results. It should be noted that the hardness increases with layers until it reaches a critical layer, layer 5, beyond which it remains almost constant. For the upper layers, for example, for 8 layer, the peak temperature always exceeds the AC1 temperature. Therefore, the hardness of those later layers was almost unchanged because martensite was untempered after re-austenization. However, for the lower layers, for example, for the first layer, the peak temperature did not exceed the AC1 temperature after the deposition of a few subsequent layers. The repeating heating and cooling below AC1 temperature gradually transformed the martensite into tempered martensite and reduced the hardness. It is evident that with the deposition of layers, the extent of tempering decreased and the hardness increased until a critical layer was reached, beyond which hardness and tempering remain unchanged.
We found that the lower layers experience multiple thermal cycles and the hardness is reduced due to tempering of martensite. But above a certain height, martensite forms but does not temper, and as a result, the hardness remains unchanged in the upper layer. This investigation provides a quantitative understanding of the tempering kinetics and the hardness variation. This same approach may be used to tailor the microstructures of other heat-treatable alloy parts. We have published this work in the Journal of Manufacturing Processes, and here is a reference to this paper.